Good morning everyone. I am DHARSANA DHARANI, working as an assistant professor in a SA Engineering College. I am from the Department of Artificial Intelligence and the Data Science. Today we are going to discuss about a crucial algorithm. The crucial algorithm was first developed in 1956 by Joseph Crucial. It was developed by a greedy algorithm and used to find the minimum spanning tree with the undirected weighted graph. Next, the basic concept of a spanning tree. A spanning tree is the subset of the undirected graph. It has the weight and the edges, and the G is equal to vertex and the edges. The spanning tree. Example. We have A is connected with a D node, and A is connected with the C node, and C is connected with a B and the Z node. The C is the mid node for all these nodes. Next, we move on to a spanning tree. The spanning tree is defined by the minimum spanning tree, and it used for the vertex and the number of edges. We have three different type of spanning tree. First, the A node is connected with a D node, then D node is connected with C, and C node is connected with both B and E. The C is the mid node for this node. Second, we move on to a spanning tree 2. The C is the center node. It connected with all the four other nodes A, B and D and E. Next, we move on to a spanning tree 3. The C is the mid node, and C is connected with both the A and B and E. The A node is connected with a D node. Next, we move on to a weighted graph. The weighted graph is the graph which have the each edges and it has the weighted value. The weighted graph means it connected with a number of weighted value. The C is the mid node for a graph, and it connected with a A. It weighted value is 7, and C is connected with a B, and the weighted value is 32. C is connected with E, and the weighted value is 23. C is connected with D, and weighted value is 9, and A is connected with D, weighted value is 10. Next, we move on to a minimum cost spanning tree. The minimum spanning tree is the subgraph of the undirected graph, and used for all the node in a connector, and it used for acyclic and the minimum total number of edges it connected with. Next is minimum spanning tree for the directed graph. First graph is the undirected graph. In a minimum spanning tree, we move to the directed graph. First, 1 is connected with a 2 node. The weighted graph of this node is 2, and the 2 is connected with the 3, and the weighted graph of this node is 3. 3 is connected with 1, and the weighted node is 10. Next, we move on to a minimum spanning tree. The 1 is connected minimum. We want to find the minimum value. First of all, we compare with 1 and 2. The minimum value is 2. First, we noted to 1 and 2, minimum value is 2. Then we proceed to 2 and 3 node. The minimum value is 3. Then we proceed to, we put a minimum value 3. Then we proceed to 3 and 1. It high value. If we connected with this node, it will find a loop. We want to reject the weighted value. This is the directed graph in a minimum spanning tree. Next, algorithm characteristics of the crucial algorithm. The crucial algorithm works under the undirected graph. It has both a weighted and the unweighted graphs. It used in the greedy algorithm to find the optimal solution of the problems. Next, crucial algorithms. The crucial algorithm is the greedy algorithm that used for a minimum spanning tree, and it is the minimum spanning tree means a subgraph that connected with a vertex and all the edges. The main graph of the possible is to find the sum of the weight assigned to each other edges. Next point is the input taken from the crucial algorithm are E is equal to V and E. The V means vertex, E means edges. V is the set of vertex and E is the set of edges, and the source of this vertex are connected with the minimum spanning tree obtained as the output given below. how does the crucial algorithms works? First, we want to sort all the edges in a graph in a ascending order. Then we want to sort in array edges. Then consider a graph and plan with a vertex in it. Then select the least count edges from the edges array, and we can find the node and make the vertex visited in all the visited graph. Repeat the step once again until we find the vertex without having any loop. And all the forming in the graph, when all these vertex are visited, we can find the minimum spanning tree. It is formed. Calculate the minimum cost of the value again and again, then the output of the spanning tree will be updated. The example for the crucial algorithm: construct a minimum spanning tree using a crucial algorithm for a graph given below. First of all, we can connect the C as the mid node for this value. It connected with a B and a D node and a F node and the G node, and the weighted value B to C is 11 and C to D is 17 and C to F is 9 and C to G is 25, and the G node is connected with A. Its weighted value is 15. A is connected with B and the weighted value is 6, and B is connected with D, weighted value is 5, and D is connected with E, weighted value is 22. Then F is connected with V and the weighted value is 10. As the first step, we can sort all the edges in the given graph in a ascending order and store the value in the array. First of all, we can find the edges for this problem. We can find the B direction to D in cost value is 5, and A direction to B is 6. C direction to F is 9 and F direction to E is 10. B direction to C is 11. E direction to F is 12. A direction to G is 15. C direction to D is 17, D direction to E is 22, and C direction to G is 25. Then construct the forest of the given graph in a single line. First of all, we want to write the node value alone in a first step. Next, from the list of the started edges cost, select at least the cost edge and it forested in the output below. First of all, we want to find the minimum value of the graph. The minimum value is first cost is 5. We want to note as the B direction to D is 5. The minimum cost is 5 and the visited array node is B and D. Next, similarly, the next least cost edges is B direction to A is 6. So we can add one output to the another graph. Next, we find the A direction to B is 6. A direction to B is 6. We can add the minimum cost. The 5 plus 6 is equal to 11. The visited array value is B and D and A. Next, the next least cost edges is C and F. C direction to F and the value is 9. Add this up to the output of this graph. Next, we want to add the C direction to F is 9. In a minimum cost, we want to add the value 5 plus 6 plus 9 is equal to 20, and the visited array and vertex is equal to B, D and A, C and F. These are the visited array. Next, the next edge we can add it into the output of graph is A direction to E is equal to 10. The minimum cost is A direction to D is 10. The minimum cost is 5 plus 6 plus 9 plus 10 is equal to 30. The visited array value vertex is equal to B, D and A, C and F, E. Next, the edge from the least count array in a B directional to C is equal to 11. Hence, we can add in it the output graph. The last node we can find is 11. B direction to C. The minimum cost we want to add all the number. 5 plus 6 plus 9 plus 10 and plus 11 is equal to 41. The visited array vertex value is equal to B and D, A, C, F and E. All these are the visited array value. The last edges from this least cost array to be added in the output graph is F directional to G is equal to 12. The minimum cost of this array, we can added all these values. The 5 plus 6 plus 9 plus 10 plus 11 plus 12 is equal to 53. We want to all these add the value, and the visited array is equal to the B, D, A, C and F, G and E. All these are the visited array value. If we find that A directional to G and is equal, the cost weighted value is 15, and the C directional to G, the cost weighted value is 17, and D directional to E is 22 cost weighted value, and C directional to G, the cost weighted value is 25. If we find that A directional to 15, if we find that the A directional to G, we find the output of this value is 15. We can find the loop. If we find the loop, mean we can eliminate the weighted value. Next, we can find that a C directional to the D, we find that the cost of this value is 17. The C directional to T, we find that the loop in this of 3 nodes, we want to eliminate that a weighted value. Next is D directional to the E, we find that our value is 22. The D direction to the E, find the value is 22. If the value we can add, the loop will be fine. We want to eliminate the weighted value. Next, we move on to the time and space complexity of the Kruskal algorithms. The time complexity of the Kruskal algorithm is O E log E, or a time complexity, and the space complexity of the value is O and vertex plus edges. The V is the number of vertex and E is the number of edges in this graph. Next, we want to see a previous year GATE question paper. Consider the following graph. Which one of this following is not a sequence of the edges added to the minimum spanning tree using a Kruskal algorithm? First of all, in this graph, we want to find the minimum value given in the graph. We want to point the minimum value, and then we want to arrange in an ascending order. Then we can find the order. First, we want to see the minimum value. The B and E is the minimum for in this graph is 2. First of all, we write the B and E. Next node, we move on to the 3. E and F, we find that a minimum value compared with both the previous node 3, 2. We want to write a 3. Next, we move on to B and C. We want to note the minimum value as the 4. Next, we move on to next. We find that a minimum value compared with a previous node is A to C. Then we move on to a next node. We compared with a previous node is F and G is equal to weighted value is 4. Last, we find that a weighted value compared with a C and D is 5. If we find that D compared with a D and a B, the node is 6 and the loop will be fine. We can eliminate the weighted value in that. Next, explanation of this problem is in the sequence of B comma E bracket and E comma F on the node, and B comma C and A comma C and F comma G and C comma D in this node, we can give an option D. All the weight are under the 3. In a Kruskal algorithm, in a minimum spanning tree algorithm, we can first order all the edges in this graph in a sorted ascending order, and we can find the minimum spanning tree and find the weight edges of this graph with a lowest weight edges. Thank you. We can see in the next section.